Hello everyone and welcome to the final video lesson for Chapter 10 of the Foundations of Scalable Systems. In this lesson I'm going to go over the main data distribution strategies that are employed in scalable distributed databases. Data distribution is a necessary strategy to scale a database system. It enables you to distribute data in chunks across multiple disks and multiple nodes. And if you do this properly and sensibly, then you can scale your data sets to hundreds and thousands of different nodes and disks. NoSQL databases are in general designed to natively scale across distributed compute nodes equipped with local storage. This is a shared nothing architecture as opposed to a shared everything architecture that is employed by databases such as Oracle's RAC. I described this in Chapter 10 in the book. With no shared state, bottlenecks and single points of failure are eliminated and performance, scalability and availability enhanced for NoSQL databases. There's one notable exception to this rule, and this typically is graph databases. Graphs are difficult data structures to intelligently partition to support high throughput workloads, and I describe again this problem in a sidebar in the book. Partitioning data, also commonly known as sharding, requires an algorithm to distribute the data objects in a logical database collection across multiple server nodes. Ideally, a sharding or partitioning algorithm should evenly distribute data across the available resources. Namely, if you have 100 million objects and 10 identical database servers, each shard will have 10 million objects resident locally. Sharding requires a shard or partition key that is used to allocate a given data object to a specific partition. This is shown on the slide here. When a new object is created, the shard key maps the object to a specific partition that resides on a given server. When a query needs to access an object, it supplies the shard key so the database engine can locate the object on the server it resides. Again, this is all illustrated on the slide here. There's three main approaches that are taken in various databases for sharding, and each database will implement one or more of these approaches, as shown on the slide here. I'll quickly go through them. Using a hash key, the partition for any given data object is chosen as the result of applying a hash function to the shard key. The result of the hash is then mapped to a partition. There are two main ways of doing this, using a modulus approach or an algorithm known as consistent hashing, which is more resilient to enable you to scale up and down the collection of nodes that you can shard across. You can also use value-based sharding. The partition is chosen based on the value of the shard key. For example, you might want to partition your data on customers based on their country of residence. Choosing the country field as the shard key would ensure all data objects for customers who live in, for example, China, reside in the same partition, and all customers who reside in Finland would also reside in the same partition. You can also use range-based sharding. Partitions host database objects where the shard key resides within a specific range of the shard key value. For example, you might use zip codes or postcodes ranges to allocate all customer objects who reside in the same geographical area to the same partition. So, partitioning makes it possible to scale out a database by adding processing and disk capacity and distributing data across these additional resources using some sorts of sharding algorithm. However, if one of these partitions is unavailable due to a network error or a disk crash, then a chunk of the database cannot be accessed. Solving this availability problem requires the introduction of replication. The data objects in each partition are replicated to typically 2 or more nodes. If one node becomes unavailable, the application can continue to execute by accessing one of the replicas. The partitioned replicated architecture is shown on the slide here. In this example, each partition has 3 replicas, with each replica hosted on a different node. There is, however, as always with distributed systems, a complication to address when we introduce replication of objects. When a data update request occurs, the database needs to update all of the replicas. This obviously makes sense so they have the same value. This ensures the replicas are consistent and all clients will read the same value regardless of the replica they access. There's two basic architectures for managing distributed database replication, as shown on the slide here. Let me briefly explain them. Leader-follower designates one replica as the leader, and it always holds the latest value of any data object. All writes are directed to the leader, which is responsible for propagating updates to the replicas. The followers are read-only replicas. Application reads can be load balanced across the followers to scale out read performance. Alternatively, we can have a leaderless architecture. Any replica can handle both read and updates. When an update is sent to a replica, it becomes the request coordinator for that update and is responsible for ensuring that the other replicas get correctly updated sometime in the not too distant future. As writes can be handled by any replica, the leaderless approach tends to be more scalable for write-heavy applications. Replica consistency turns out to be one of those thorny distributed systems issues that we always have to address. The core of the problem revolves around how and when updates are propagated to replicas to ensure they have the same value. The usual issues of varying latencies between nodes and network and hardware failure make this a totally non-trivial issue. If a database can ensure all replicas always have the same value, then it's said to provide strong consistency, as all client accesses will return the same value for every data object. This implies the client making the update must wait until all replicas are modified before an update is acknowledged as successful. This, of course, introduces latency. In contrast, a client may not want to wait and only wait for one replica to be updated and trust the database to update the others as soon as it can. This means you have a window of time when replicas are inconsistent and reads may or may not return the latest value for other clients. Databases that allow replica inconsistency are known as eventually consistent. The trade-offs between strong and eventual consistency and how design choices affect scalability and availability are dealt with in detail in the video lessons for chapters 11, 12, and 13 of the book. This discussion of consistency brings us nicely to the CAP theorem. Eric Brewer's famous CAP theorem elegantly encapsulates the options you have for replica consistency and availability when utilizing distributed databases. It describes the choices a database system has if there is a network partition, namely when the network drops or delays messages sent between nodes in the database. Basically, if a network is operating correctly, a system can be both consistent and available. But if a network partition occurs, a system can either be consistent, known as CP, or available, known as AP. This situation arises because a network partition means that some nodes in the database are not accessible to others. The partition splits the database into two groups of nodes, as shown on the slide here. If an update occurs and the replicas for the updated data object reside on both sides of the partition, then the database can either return an error as it cannot ensure consistency because it can't update all of the replicas, or it can apply the update to the subset of replicas that are visible. This is AP. This means there is replica inconsistency until the partition heals and the database can make all replicas consistent. Until the consistency is resolved, clients may see different values for the same database object depending on which side of the partition they can access. You'll see this AP or CP categorization used for different NoSQL databases. It's a useful but not totally meaningful, as most databases, as I'll explain in later lessons, make it possible to tune configuration parameters to achieve AP or CP to meet application requirements. So the CAP theorem is a useful model to use to think about how databases, replicated partition databases, behave when partitions in the network occur. Reality, however, is a lot more complicated because databases will allow us to tune their behavior based on the availability and consistency needs that an application has. And we'll talk about these in the next section. That completes the video lessons for Chapter 10 of Foundations of Scalable Systems. In the next set for Chapter 11, we'll start delving much more deeply into the issues associated with eventually consistent databases. Thanks for watching.